So, in the last lecture we talked about the role of aerosols and how difficult it was to estimate impact. And one of the difficulties is the way aerosols interact with clouds. Okay? That is the biggest problem. To illustrate that, I have shown one simulation by Seinfeld, published in Proceedings of the National Academy of Sciences a few years ago, and they are comparing 3 simulations by the same model. This model is the well known GFDL model from Princeton, where Professor Manabe worked, who got the Nobel Prize for his modeling work. And so, they have done 3 simulations. Okay. So, for example, CM3W, which is the red line, increased cloudiness owing to reduced auto conversion of cloud droplets to rain. Okay. Okay. Then there are 2 more simulations which had a slightly different assumption. Okay. So, CM3W, CM3 and CM3C had different assumptions about how clouds are affected by aerosol. Okay. And they get 3 different solutions. Okay. The red one shows a global warming by 1 degree by year 2000, while the blue shows a warming by only 0.6 degrees. So, you can see how sensitive the prediction of a climate model is to your assumption about how aerosols affect clouds. So, there is going to be continued uncertainty about how aerosols impacts our climate, because we still do not understand how aerosols interact with clouds to change either the cloud number of droplets of clouds, or the cloud droplet radius, or the cloud lifetime. All these are influenced by aerosol. We do not fully understand all these processes. There is research still going on, but there is no agreement among different groups. So, because of that, this large uncertainty you see here will continue to be there in our future projections. Now, I will briefly talk about natural aerosols. Human beings release aerosol by industrial activity, but nature also sometimes releases a large amount of aerosol due to volcanic eruption. Sulfur dioxide is the major component, and it becomes sulfuric acid and then sulfate aerosol, then which reflects sun's radiation. So, whenever there is a large volcanic eruption, you will get a lot of cooling, because volcanoes erupt with great vigor, and these sulfur dioxide particles reach the stratosphere at the height of around 20 kilometers, and those sulfate aerosol reflect sun's radiation and hence cool the earth for the next few years. Okay. Here is an example of various eruptions over the last 100 years from 2 different groups, and you can see that they are not same, because after eruption occurs, you make an estimate of how much is changed the aerosol optical depth, and that estimate is not perfect, because based on the composition of the aerosol released by the volcanoes, you have to estimate how much is the total amount emitted. You can see in the last 60 years the agreement is not too bad, although the peak emission is a little different, but if you go back 100 years earlier, there are much larger differences. Okay. So, this is a fact we have to live with when you deal with volcanoes. Now, here is an example of reduction in radiation transmitted due to aerosol emission, and typically on a clear day about 94% of the solar radiation in the visible region around 0.5 micron is transmitted in Hawaii, but when there was aerosol it came down to 0.74 for a short time, few months, then it came back. That was El Chichon, and that was here Pinatubo, and earlier to Agung. Notice that there is a lot of difference between the different eruptions because it depends on the amount of sulfur dioxide emitted in tons. Okay. Again, for a small emission, so it did not have too much impact. El Chichon was larger, even larger than Pinatubo. Okay. Here is one simulation of the Pinatubo eruption, and it is shown here just to illustrate how the world cools immediately after the eruption. If in the GCM everything is included, including water vapor, there is much larger cooling of the order of 0.6 degrees, but if you do not include the water vapor feedback, you suppress it, then the cooling is much less. So, this is the water vapor feedback. As soon as cooling occurs, the amount of water vapor in the atmosphere goes down. Okay. In the case of greenhouse gases, it went up. In the case of aerosol, which cools the atmosphere, it will go down. Okay. So, it has the opposite effect. The cooling of the earth causes the water vapor to go down, and there is more cooling. Okay. So, this was close to observation, and so this shows that the models are quite good at taking care of the impact of aerosol emission. Now, here is another example of the reflected solar radiation due to Pinatubo eruption. These are the two estimates from satellite measurements, and these are model estimates of the extra radiation reflected to space. You can see that some models are quite good. They are coming between two of the estimates from satellites, but there are other models which are not so good because these models did not include natural aerosol from volcanic eruption. Okay. If you include that, you do better, but of course, some models are not as good as other models. So, this shows that today models which include volcanic eruptions do quite well, okay, to produce the additional radiation reflected to space by the volcanic aerosols. Okay. There is another example from another paper where they varied the amount of emission by Pinatubo. Pinatubo emission was actually quite small, that is why it caused only 0.5 degree cooling, but if it had been 100 times higher, it would have caused about 12 degree cooling. So, some of the eruptions during the last 1000 years were quite high, and in some cases I am talking about not now, but in the distant past millions of years ago, some eruptions were so high that they could have caused 12 degree cooling, and that could have pushed the earth into an ice age. So, this hypothesis is still being debated. You know that most of the ice ages that occurred in the last million years were due to the changes of earth orbit around the sun, but if you go back beyond a million years, there have been events of large volcanic eruption, especially 65 million years ago, and those eruptions were so large that they could have caused an ice age. That possibility is still there, although we do not have very good evidence to actually demonstrate, because we do not know the quantum of aerosols that was emitted by those major eruptions. Okay. But this is a simulation which shows that large cooling is possible. Okay. And I kept here in the slide various technical terms related to aerosols, which some of you may want to see. We want a clarification about some of those roles. Okay. Finally, I want to end the discussion on aerosol by pointing out that although our ability to predict the impact of aerosol is somewhat limited because of the complexity of the effect of aerosol on climate, but the impact of aerosol on health is well established. It does not matter what you inhale, black carbon, sulfate or whatever other thing, if you smoke, all of them have adverse effect on your health. Okay. This is well established with a lot of data, especially from cigarette smoking, and we know it causes chronic respiratory disease, and In India, that is the dominant thing. In other countries, it is somewhat less. I am talking about deaths per 100,000 people. So, 94 deaths per 100,000 people in India, but in other countries somewhat less. So, this is well established, and we know that the mortality is due to the impact on the lungs, impact on the blood viscosity, its impact on heart rate. Okay. People have measured the impact on heart rate by people going in cycles in urban areas which high air pollution. You can see an immediate impact on the heart. The heartbeat starts fluctuating. Okay. Blood pressure goes up. Okay. And the deposit of plaques in the blood will go up. So, we are 100% sure that air pollution's impact is already there on our health, and it is equivalent to death of over 1 million people per year in India. So, we need to reduce air pollution immediately, but that will have some impact on the global warming, which is unavoidable. Okay. So, with that I will complete my talk on aerosols, and I will move on to the more important issue about how to predict climate change. I have already talked about various models which have been used to predict climate change, but it is important for you to know how good or how bad these models are, because if you want to predict the future, you cannot use statistics of the past, because past is very different from the future. What happened 1000 years ago, we discussed that when we discussed the past climate change from the last ice age to the present. We have understood how those things happen, but that cannot be used as a basis for predicting what will happen in the future, because future is very different from the past, because future climate change is occurring rapidly. The past climate change was slow. It was useful to tune our models, but it cannot be used as a basis to predict the future. So, we need to look at climate models. So, I will start the discussion on climate models, okay, and we move on to the discussion on what I call as strengths and limitations of models. As I already pointed out, we need climate models to predict the future. There is no alternative. There is no other way to predict the future. But you also know by now that climate models make many approximations to model the complex earth system, okay, especially clouds. Even today, the modeling of clouds is not very good. Okay. It has improved a lot in the last 40 years, but it is still not perfect. Okay. And we know that because of the fact that the models have resolution of typically 50 by 50 kilometer grid, they cannot resolve anything happening inside that grid. So, there are uncertainties because of that. So, we cannot trust any one model and its simulation. So, we need many simulations to take care of the chaos in the system, and as well as use many models, so that whatever errors are in the models cancel out. Okay. So, that is the basis of all future prediction. Multiple simulation by a single model plus simulation by many models are all put together. So, I want you to understand how good or how bad the models are. Now, I need to do that because over the past 30 years, during the discussion in the Intergovernmental Panel on Climate Change, we had to defend climate models with the climate change deniers, who argued that because models are not very accurate, we cannot believe that the global warming which has occurred over the last 150 years is due to human beings. So, we all argued vehemently and with a lot of data that we are quite sure that the global warming of 1.5 degrees centigrade is primarily on account of human actions. But there we are talking about global mean temperature. Global mean temperature can be easily predicted. We started our discussion in this course by a simple model in which we had only 4 parameters to decide global temperature. That was the incoming radiation, Earth's albedo, greenhouse effect, and how much radiation atmosphere absorbed the sun. These 4 parameters were able to tell us why Earth was at 15 degrees centigrade. Okay. So, as far as global mean temperature is concerned, in spite of all the limitations of the models, global mean temperature can be simulated fairly well, okay, across 30-40 models. But remember, then when you want to predict future climate change, the impact of increasing greenhouse gases, we need to worry about regional climate change. Because when you talk about impact, none of us are concerned about global mean temperature. Global mean temperature was a metric used for global negotiation to come up with how quickly to reduce CO2 emission. It is not used for anything else. Global mean temperature does not tell me what will happen to climate of Bangalore 10 years from now. Okay? So, when you talk about impact on climate, you have to focus on regional climate, not global mean, and it is where we have problems. The model's ability to predict regional climate is not as good as the global mean temperature. Okay? I want you to understand that very clearly, because a lot of non-governmental organizations which work on actions related to climate change, they sometimes confuse these issues, and many of them tell the public that models can predict accurately what will happen in your district 30 years from now. That is not possible, because to get that accurately, the models have to improve much more, and you need to specify the changes in aerosols, changes in land cover and other things at the regional scale. Okay? If I do not have a good idea about how Bangalore will grow in the next 30 years, how much of concrete will be added, how much of greenery will be reduced, how much air pollution will be controlled, one cannot predict the climate change in Bangalore 30 years from today. Okay? So, this must be understood very clearly. On the one hand, we are very confident about the global mean temperature. On the other hand, we are not so confident about the temperature change in a district or in a city, and more importantly, we do not know much about changes in rainfall. As human beings, we are concerned not only about temperature, but much more about rainfall, because rainfall causes floods. If rainfall does not occur, it causes droughts. Both droughts and floods are issues of our existence. If there is a long drought in India, we will be in deep trouble. If there is a lot of heavy rainfall events, heavy floods have caused huge losses and loss of life in India. So, those are not easy to predict. Okay? They can be predicted in the short term. For example, our weather forecast models are pretty accurate for the next few days. So, you can trust them if they tell you that it is going to rain heavily in the next few days, and you have to take precautions. For example, the prediction of the track of cyclones is very accurate. So, many thousands of lives have been saved by weather forecast models which accurately tell you where the cyclone will hit on the land. Okay? If you recall, 30 years ago, when a cyclone landfall occurred over Orissa, there were lots of deaths because the track prediction was not accurate. Today that has been avoided because of good short term prediction. But if you ask me what will be the track of cyclones in the Bay of Bengal 30 years from now, I cannot make an accurate prediction. So, I wanted to appreciate the difference between global mean temperature prediction and the local temperature and rainfall prediction that is relevant to you and me. Okay? So, this is a point I want to elaborate so that all of you are able to distinguish between how good the climate model is in the global mean temperature and how limited our ability is in the local temperature and rainfall. Now, what you want to understand in modeling, this comment by William James is relevant. Modeling involves simulating the reality. We do that with a series of approximations. So, the last 50 years our approximations have become better and better, and we are approaching the reality in the simulation, but we have not reached a level where these models can be used for long term prediction of impact of climate change in cities. So, again I will repeat, we need climate models to test our understanding of climate system, for prediction of the climate change, and for attribution of the cause of climate change. For example, 2023 was a very warm year. Okay? We need to know why. So, a lot of people are doing simulations for last year to understand how much of the warming was due to human induced greenhouse gases, human induced reduction in aerosol, and how much of it was due to El Nino, which is a natural climate variation that occurs in the Pacific. For that we need climate models in which you can remove aerosol, put aerosol, look at all these and ask yourself, can you explain the large warming last year? Now, climate models have come a long way in the last 60 years, and the credit goes to Professor Manabe, who started the climate modeling more than 60 years ago. Okay? And he, along with Hasselmann, who did ocean modeling, and Giorgio Parisi, who was a physicist who did work on stochastic modeling, all these three were awarded the Nobel Prize because they improved our understanding of the Earth's climate. Okay? So, we are mainly dependent on what we have done over the last 60 years. But remember that all models are wrong because they are approximating the real, but they are still useful. Okay? Since the Earth system is complex, every climate model has some approximation that they make, and these can cause serious errors in either predicting a flood or a drought. So, this must be understood. So, I want to end this lecture by a comment from a famous Professor Michael Mann, about whom I will talk later. He says climate models are fuzzy rather than clear crystal ball. They provide important guidance in many aspects, or best guidance, drawing upon the laws of chemistry, biology and physics. That is a whole lot better than opinions and hunches and wild speculation. For example, the overall warming is very much in line with the predictions, but still they are fuzzy. So, this point I want to elaborate further in the next lecture. Thank you.